Hey guys, how's it going? Welcome back to Pre-Calc with Passmore. Today we're gonna start section 7.3. I was gonna just bust out the whole thing, and then after I was going through it, I realized that for those of you that are still along with us here in this distance learning times, that this can sometimes be a lot to digest, and you guys have a lot of other stuff going on. So I decided to continue to break it up. For section 7.3, I'll probably do the same for 7.4 because these really start to add on to our mathematical tool belt for different ways that we can solve trig identities, verified trig identities, disprove trig identities, all that jazz. So today is section 7.3, day 1, the sum and difference identities. Today we're only going to focus on cosine, and then tomorrow we'll develop sine and tangent. So our learning objective is, let me hide this, develop and use the sum and difference identities for cosine. So we're going to work with just cosine today, see a couple examples that you guys are going to work through in today's problem set with me. And then I gave you guys some practice problems. And yeah, hopefully you start to feel pretty comfortable. These ones are nice because they're more applied. So you get to go back and use numbers instead of just substitutions, which is really cool. I'm feeling so much better, so I think I'm going to make a quick little disproof video for you guys in case you were struggling with that. I know a couple people were kind of having a hard time wrapping their heads around that, and I think once you see what my intention was, you'll be like, oh yeah, I like disproofs because again, you're working with a more applied sense, you're using actual numbers, it's just your choice, and things like that. So you might be wondering why I have a picture of some stars and a triangular type thing on here. We'll get to that in a second. So let's dive right on in, shall we? So sum and difference formula uses. So the reason this all came about to have these types of formulas that we're going to be discussing today is because it was originally developed to study the motion of the celestial bodies, to study how things are moving in space and why they're moving and where their final destination will be and things like that. So what up, Kepler? Johannes Kepler, we see you. We know what you were doing. We vibing, right? And we're going to continue using it today. So that was obviously a bajillion years ago. But also they are sum and difference formulas are used to find derivatives of trig functions. So those of you moving on to calculus, derivatives, huge in first semester, integration, huge second semester. But the derivatives of trig functions end up becoming these sum and difference formulas. So they're very, very familiar. It's also used in complex number theory. So remember when we started to talk about the complex number plane? Let me grab my laser pointer. Right over here, right? This is the real axis. This is the imaginary axis. And this is the angle phi with our radius. This point can be expressed as x plus iy, z bar, x minus iy, so it's used in complex number theory. Also, since we're talking about trig, it's the study of wave motion, like the whole thing, reason why I brought up trig is sinusoidal waves. Also, more specifically, what we're going to be using it for is to find exact results of non-standard angles. So like an angle we don't know, like, I don't know, 12.4 degrees or something like that. We are able to find exact results of it without using a calculator in radical form with no decimal approximations. And we are using this to put in our tool belts right here. So this is our math tool belt. Strap it on. And we're going to use this to continue our journey with trig identities, trig functions, proving, disproving, all of that fun stuff. The things that bring me the greatest joy. So before we get into it, and the example specifically, you guys kind of have to have an idea of where did this come from, because otherwise it doesn't really make any sense and the formula is really ugly and crazy looking. And I'm kind of going to break it down in layman's terms. I'm not going to go too in depth. If you're really, really curious about it, it's in the text, it's all over the web, you can do it yourself, but I just kind of want to get to the bulk of it. But the general understanding of where it came from and why it's here is really important. So as always, you guys know that I'm super huge on you guys having a visual representation, a visual understanding of what's going on. Where are we in the unit circle? What quadrant are we in? What do, our X values represent? What do Y values represent? All of that jazz, right? So going back to our unit circle, starting with the unit circle with the center C. So we're going to label the center C. Normally we don't label it. Consider the point A on the terminal side of angle A, and consider a point B on the terminal side of angle B, seen in figure 7.9, which I'm going to throw up in a second. Essentially, point A, we're just picking a point. Here, let me throw it up. Here's point A, right? Picking any point in quadrant 1. Point A has angle measure alpha. And any other point, it doesn't matter which side it's on, point B has angle measure beta, right? If we were to draw those triangles, if we dropped this perpendicular bisector right here, this angle would be beta, this angle would be alpha. So we've got this image going on here, right? This is our unit circle. We know that our radius is 1 because it's a unit circle. I've just got 2 points within my arc, right? Here's my center labeled C. Since we have a unit circle, we've got radius 1, and then we also know how to represent these points. Remember, the points are x comma y, and cosine is x, so we're going to have cosine of the angle alpha, comma, sine angle alpha for point A, right? Alpha is the angle measure that goes along with A, so it's cosine sine of that particular angle. Similarly, we're going to have cosine sine of angle beta, which represents the angle for point B, right? So I've got, not only do I know that this is 1, but I know that I can represent this point as cosine alpha, sine alpha. I can represent this point as cosine beta, sine beta. And we've got this little visual going on here, right? Nothing too crazy. Now, I want to find the distance of this line segment right here from A to B. The distance of this line segment. I want to know how big is it, right? For any line segment AB, for any points on my unit circle. So in order to calculate that, we're just going to use the good old distance formula. Again, I'm going to spare you the nasty details of working this out just for the sake of time, for the sake of clarity as well. I'm not going to bog you down with that, but if you're interested, it's in our text. I'll go over it with you if you really want. Maybe during office hours or something like that. But I think you guys are going to be cool with me sparing you the distance formula. So we're working it out with both of those points, cosine alpha, sine alpha, cosine beta, sine beta. And essentially what it boils down to is this. The segment AB, right, this length, the distance between these 2 points, AB, is equal to the square root of 2 minus 2 cosine alpha, cosine beta, minus 2 sine alpha, sine beta, right? So I have that this line segment is this nasty piece of information, right? Or it looks rather nasty initially. Aren't you glad I spared you the distance formula proof? So I have this, right? And you're kind of like, okay, cool. But there's one point specifically in this quadrant that would be rather interesting to know about with a similar diagram. So we're going to go ahead and do that. So if I rotated that entire sector, right, this is a little sector right here. If I rotated it clockwise until point B is on that quadrantal point 1, 0, we're going to get this figure. So I was here, right? This is point A and this is point B, and I'm rotating it clockwise so that this point B is this known value here. I know that this is 1, 0 just as much as I know that this is 0, comma 1. And this is negative 1, 0, and this is 0, comma negative 1, right? But it's interesting because this is a nice number to work with. So I'm going to completely rotate that segment however many degrees I need to until it's down here. And I've got point A and point B here. Point B just happens to reside on the quadrantal point 1, 0, right? And this angle measure is alpha minus beta. And then similarly, our point here is going to be cosine of alpha minus beta, sine of alpha minus beta, because I'm moving in that direction towards that. So I have some new coordinates, still going to be in cosine comma sine format because that's how we work in trig life. But the distance hasn't changed. right? I literally just performed a rotation. Nothing changed. This distance is exactly the same as it was before. So if I use the distance formula again, but with these new coordinates instead of all the crazy ones, I've got a nice little simplification happening here. If I perform the distance formula again, I end up with this result. That segment is equal to 2 minus 2 cosine alpha minus beta. A lot nicer, a lot more simple. Now you might be wondering, well, what's the purpose in this? What is the point of this? And something I want to bring up is, remember, alpha used to be all the way up here, beta used to be over here. In order to find this value, that would be that whole arc alpha minus that arc value of beta to leave behind this segment here. So that's why we have that value. And you might be asking, well, why did we just do that twice? Well, I'm trying to come up with the cosine sum formula. I'm trying to figure out what happens when you add two things together. So this is just a really tricky manipulation that somebody came up with way back in the day, and it gave us this wonderful trig identity. But in essence, we have a distance formula for this line segment, AB, and we also have a distance formula for this line segment, AB, where B is at our quadrantal point, right? Now remember, see, here's our two images. I've got this guy right here, and I've also got this guy. They have just been rotated. Nothing has changed. But the distance, I have two different formulas for distance, except they're representing the exact same thing, right? So since the distance is the same for both segments, we can set them equal to each other. So if I do, I have my nice little short guy over here, and my long, seemingly large formula here, right? I know that AB has not changed. All I did was a rotation, so I can set them equal to each other. And with a little bit of algebra, we are going to get our cosine sum formula. So I've got the square root of 2 minus 2 cosine alpha minus beta is equal to square root of 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Right? If I square both sides, I notice they both have square roots. I end up with 2 minus 2 cosine alpha minus beta equals 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta, right? All I did was square both sides. Upon further inspection, I notice that this guy has a 2, and so does this. So whatever I do to the left-hand side, I can do to the right. So if I subtracted 2 from both sides, what's left behind is negative 2 cosine alpha minus beta equals negative 2 cosine alpha cosine beta minus 2 sine alpha sine beta, right? All I did was square both sides, subtract 2 from both sides. As long as I'm doing things on both sides, I'm preserving equality, and I know these two things are equal based on my construction. Cool. So upon further inspection, let's look a little bit further here. What does the left-hand side have in common with the right-hand side? A simple arithmetic calculation that I can perform that's going to simplify this expression even further. I have negative 2 cosine of alpha minus beta equals negative 2 cosine alpha cosine beta minus 2 sine alpha sine beta. I notice that there's negative 2 right here and negative 2 in two different spots. So if I divide by negative 2 on both sides, that's going to free up some space, isn't it? What's going to happen is the result is I get cosine of alpha minus beta on the left equals, divide by negative 2, cosine alpha cosine beta. This becomes a plus sign because negative divided by a negative is positive, sine alpha sine beta. And this is a difference identity for cosine because you have the difference of two angles for cosine. Cosine of one angle minus another is equal to this value. And this is precisely what I was trying to get at. Okay, so this is the difference identity that we're going to be using. Now, if we substituted in negative beta into this equation, the difference identity, we'd get the sum identity. Again, I'm going to spare you because I actually want us to just practice using them and get comfortable using them. So if I did that, I would get the sum identity for cosine is cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. So I want you guys to get comfortable with that. Notice that we start off with cosine and with sine, whatever this sign is here. So this is a negative. It's going to be opposite in between cosine sine. Similarly, whatever sign is in the middle here, this is positive. It's going to be opposite between cosine and sine of both the alphas and betas. Both of my alphas and betas, alpha, beta, alpha, beta, alpha, beta, alpha, beta. So I want us to use these. This is what we're going to be using all today. And then tomorrow we'll develop sine and then tangent as well. But yeah, so let's get to using them. So the uses of the sum and difference formulas for cosine is that we can find exact values for trig functions for certain angles, expressions, and establish additional identities. We're going to establish the additional identities tomorrow from this, but we're going to use it and put it to action and find some real values, which I think you guys are going to like. So first example, there's 3 today on our problem set. We're going to find the exact value for non-standard angles. So we don't know what 15 degrees, cosine of 15 degrees is, because cosine of 15 degrees is not on our unit circle. We have 30, we have 45, and then we have 60, 90, right? They're all in increments of 30, 45, 60, 90. So if I asked you to figure out what cosine of 15 degrees was, we need some other way to establish that. And this is where our sum and difference are going to come into play. So this example says use the sum and difference identities for cosine to find the exact values for, let's work on problem A, cosine of 15. And I know that I can rewrite this as cosine of 45 degrees minus 30. And these are 2 known values that I can use, right? So we're going to start off by using the difference identity directly. Notice that this is a difference. So that's kind of my clue is, oh, I'm going to use my difference identity. So let me just write out the difference identity. Cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. I'm going to use this right-hand side. I'm going to expand this out and use it to figure out what cosine of 15 is equal to exactly. So I notice I have cosine of 45 minus 30. If I rewrite this into the expanded right-hand side, I notice that alpha is going to have to be 45 because it comes first. Beta is going to have to be 30 because it comes second. Both of them are positive because this is a minus sign, and that's the difference that I'm talking about. So I end up with cosine of alpha, or cosine of 45 degrees, times cosine of beta, or cosine of 30, plus sine of alpha, or sine of 45 degrees, times sine of beta, or sine of 30 degrees. Now, this is where real good stuff starts to come into play, because we know the cosine and sine of 45 degrees and 30 degrees. Those are our special trig values that we know from our unit circle, right? Cosine of 45 is rad 2 over 2. Cosine of 30 is rad 3 over 2. Sine of 45 is rad 2 over 2. And sine of 30 is 1/2. So I literally just plugged in cosine 45, here's the value. Cosine 30, here's the value. Sine 45, rad 2 over 2. Sine 30, 1/2. Those come directly from the unit circle. And then this just becomes arithmetic, right? Rad 2 times rad 3 over 2. They have the same common denominator. I want to keep that. So I'm going to multiply these radicals by properties of radicals. That's going to be negative radical 2 times 3 is radical 6. And then 2 times 1 is radical 2. So I end up with rad 6 plus rad 2 over 2 is my result from here. Now, also a property of radicals is you cannot add them unless they look exactly the same. So this cannot be simplified any further. This is not going to become rad 8. Be careful. It's just going to stay rad 6 plus rad 2 divided by 2. Nothing I can do further there. So I know cosine of 15, which is what I was trying to find out in the beginning, is equal to rad 6 plus rad 2 over 2, just by using my difference identity directly and some things from my unit circle. It wasn't so bad, right? Like, we get to go back and use things that we know. So like I said, I think you guys are going to like this section a little bit more. Now, let's try problem B, shall we? Let's find cosine of 75. Again, this cosine of 75 degrees is in quadrant 1. But it's not one of our special trig functions. So it's past 60 degrees. It's an extra 15, right? But 15 degrees, but I don't know that exact value on my unit circle. Like, it's not going to be rad 2 over 2 or root 3 over 2 or 1/2 or any of those values from my unit circle. So we're going to use the sum and difference identities. So this one was given to us, but we can rewrite cosine of 75 as cosine of 45 degrees plus 30, because 45 plus 30 is 75, right? Notice that now I have a sum here, so I'm going to actually use the sum identity. It's going to be almost exactly the same, but I'm going to use cosine sum identity in order to solve this guy, because this is a sum, right? I used a difference identity here because I had a difference. I have a sum here. I'm going to use the sum identity. So the sum identity is cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta, right? Simple enough. I know my alpha is going to be 45 degrees, my beta is going to be 30, and I'm going to plug it right on in here. So cosine of 45 degrees plus 30 is going to be cosine alpha, or cosine 45 degrees, times cosine beta, or cosine 30 degrees, minus sine of alpha, or sine of 45 degrees, sine of beta, sine of 30 degrees. Alpha always comes first, beta always comes second. Now let's continue working with the right-hand side of the equation, since these 45 and 30 degree angles I know pretty well, and I know I'm going to know the exact value of cosine and sine for both of them from the unit circle again. So cosine 45 degrees is going to be rad 2 over 2. Cosine of 30 is rad 3 over 2. Sine 45 is rad 2 over 2. 45 is the best because it's always just rad 2 over 2. And sine 30 is 1/2. Performing the same thing, rad 2 times rad 3 is still going to give us rad 6. 2 times 1 is still going to be rad 2, except now I have a difference. So I have rad 6 minus rad 2 over 2. Again, properties of radicals, I cannot say this is rad 4. This is not the square root of 4, which reduces to the number 2. So be careful, beware. If you're not sure, go back and look at your properties of radicals. That is definitely not something we teach you that you can do in Algebra 2. Therefore, cosine of 75 degrees is rad 6 minus rad 2 over 2. And you could use your calculator to get a decimal approximation, but remember how I said at the beginning of the semester, we're going to kind of veer away from our calculators a little bit and get into exact values because we're not trying to have decimal errors. This is precisely what we set out to do. We found the exact value of cosine of 75 without using a calculator to tell us what that number is. We gave you an exact value, which is pretty neato. Cool. So, alert! Alert, alert, alert!
Psh, can you hear me? We have a major alert to bring to your attention.
Okay, so now that I have your attention, please do not fall for this. Just because I'm using these identities does not mean that cosine of 60 plus 30 is equal to cosine of 60 plus cosine of 30. I'm using a special identity to be able to use these things. But know that like 60 plus 30, cosine of 90 degrees is 0. 0 does not equal 1/2 plus rad 3 over 2. Do not make this assumption. Kind of like when we were doing disproofs, proving something is not an identity. If it looks too good to be true, like this would be too good to be true, it probably is. In general, f of a plus b does not equal f of a plus f of b. It's actually very, very rare that you would find something that works out like this to be perfectly, to work out perfectly. It's kind of like when people are squaring a plus b, they say it's a squared plus b squared. No, that's not true. So it's also the same with adding our trig functions. This is not a true statement. So although we're doing some pretty cool manipulations, do not get hopped up that these are the same. Okay? Common misconception. It happens. I just wanted to bring it up so that we kind of had a little context. And now you know. You've been warned. You have had the life alert. Now you've been alerted that this is not allowed. Fake news. This, I forgot I added that. Fake news. This is not true. All right. Let's do another, let's sum this up, then we'll do some more examples. So, the sum and difference identities for cosine. I'm going to introduce some notation to you that might look a little weird, but I think you guys will be comfortable with it. So, we know the sum would be cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. And similarly, a difference would be cosine of alpha minus beta. It's cosine alpha cosine beta plus sine alpha sine beta. peep this, these new expressions. I'm sure you guys have seen plus or minus, but have you seen minus plus? These signs flip within the equation depending on what we're working with. So if I start off with the sum over here, I have a difference on my right-hand side. If I start off with a difference on my left-hand side, I'm going to have a sum on my right-hand side. So this top one corresponds with this top value. This bottom value corresponds with this bottom value as well. And this is essentially just a shorthand for sum and difference identities. So instead of writing it out twice, I can write it once, just making sure that I have both of these plus or minus and minus plus arithmetic pieces of information here to kind of consolidate all of the formulas that we have, because we have a lot and we ain't done yet. No, we ain't. Also, we can do the backwards too, right? I can go from this expanded stuff, since this is an identity, I can go forwards from left to right, but I also can go from right to left. So this is just rewriting it with the right-hand side first equals the left. But something to keep in mind with identities, with any identities we have proven thus far or we have in our tool belt, we can use it both in the forward direction and the backward, right? We have established that that equality is maintained. We have either done a proof already or I've told you that it's an identity. So you can use this to your advantage depending on what you're working on. So we can use this to expand an expression, right? This is condensed and we expanded it out to figure out a specific value. Or if we're given something ugly like this to begin with, we can contract it into this beautiful little precise little package over here as well. So it goes both directions since it's an identity. That's the reason why, nothing else. Unless something's an identity, you can't do that, all right? So let's do example 2. Use the sum and difference identity to simplify this expression. So we're going to simplify, right? So I just told you guys that we could expand it or we could simplify. Here's an example of us simplifying. So write as a single expression and evaluate. So not only does it want us to write it simply, but then it wants us to tell us the exact value of it too. So this is what I mean by this is expanded out to begin with. Cosine of 57 degrees times cosine of 78 minus sine of 57, sine of 78. Again, 57 and 78, those are not known values that we have on the unit circle. We have no idea what cosine of 57 degrees is unless you use your calculator, or cosine of 78 and vice versa for sine, right? But now I can use an identity to my advantage and I can find it exactly without the use of the calculator. And as a matter of fact, it would be even more accurate than the calculator approximation. Oh, we're going to begin by using the sum formula. If I'm working with this piece here, notice that I have a difference, and this is the expanded out. So since it's minus, I have to use the sum, because remember in our formulas, they were off by a value. They were off by a sign. So since this has a minus sign, I'm going to use the sum formula. And so I just rewrote the problem, cosine of 57 times cosine of 78 minus sine of 57 times sine of 78. I want to use the sum formula. And notice that this number comes first, so that's going to be alpha. Alpha is degree 57, beta is degree 78. So if I use my sum formula, cosine of alpha plus beta, I have cosine of 57 plus 78. That's pretty cool. And if I added those two together, I get cosine of 135. 57 plus 78 is 135. So one, I have simplified this expression. Cosine of 135, that's the first part. I wrote it as a single expression, right? So this hubbubaloo over here is literally just cosine of 135 degrees. So I simplified it. And then let's think about cosine of 135. 135 is past 90, but below 180. So it's going to live in quadrant 2. And actually, we know this exact value because it's in quadrant 2 and it's a perfect value on the unit circle. It's actually, oh, let me draw. Let me draw a really bad drawing. You ready? So that was actually a pretty solid line. It's in quadrant 2 It's actually right over here, and it's 90 degrees plus 45. This arc right here, that's 45 degrees. Oof. And so this angle measure here, this point right here in quadrant 2 is 90 plus 45. That's 135 degrees. We know that exact value. So that exact value is actually rad 2 over 2, but we're in quadrant 2, which means x is negative, y is positive. Cosine is the x coordinate, so it's negative rad 2 over 2. So this was me simplifying my expression. This is me evaluating my expression exactly without a decimal approximation. That's not too bad, right? So using the information that we know, we can go from expanded to simple. And then we could say exactly what that is if it's a known value on our unit circle. Got another PSA for you guys. Public service announcement. Public service announcement, all right? The sum and difference identities can be used to evaluate the cosine of the sum of two angles. So you can use it to evaluate cosine of two angles, even when they're not next to each other, when they're not adjacent. So if you got to add up two angles, just like we did in this last example, I'm adding 57 and 78. They're not close to each other on the unit circle, right? They're not even next to each other. I can use the sum and difference identities to evaluate that sum, even when they're not next to each other, or even if they're not expressed in terms of cosine. So that's why this is so clutch, right? I can use these sum and difference identities to not only evaluate two angles that aren't close to each other, and they're being added together, but it might not even be in terms of cosine to begin with, and I can still use this. I can kind of finagle my way and figure that out. So this is kind of like why these are so cool in a sense, is you can do so much with them when at first it seems like you can't. So this is our last example for the day, computing the cosine of a sum. And this is kind of like a little bit of a two-parter. So let's see the sitch we've got here. Given sine of alpha is the ratio 5 over 13, with the terminal side of alpha ending in quadrant 1. So sine is 5 over 13, it's in quadrant 1. Tangent of beta is negative 24 over 7 with terminal side of beta in quadrant 2. So I've got an angle alpha in quadrant 1, an angle beta in quadrant 2. Alpha's in terms of sine, tangent or beta is in terms of tangent. So this is not in terms of cosine. Also, sine is not in terms of cosine. This is what I'm saying in that last example. When they're not expressed in terms of cosine, I can still use it. My goal is to compute the value of cosine of alpha plus beta. So it didn't even give me the angle. It just told me the ratio of sine of alpha is 5 over 13 and tangent of beta is negative 24 over 7. So I kind of need to do a few things here. In order to use cosine of alpha plus beta, one, I'm going to have to use my sum identity because this is the sum, right? So I'm going to need cosine alpha, cosine beta, sine alpha, sine beta. But I'm also going to need to figure out what alpha and beta are to begin with. So because I'm using this identity, I need cosine alpha, cosine beta, and sine beta in order to expand this bad boy out, right? So a good frame of mind is to figure out what we need, right? I need those four things in order to just be able to work with this expression right here, in order to be able to use my sum of cosine identity. Then I need more information because in order to have cosine alpha, cosine beta, sine beta, I also need more information from here. Maybe I don't even need alpha or beta directly as I can use the ratios, but I need to draw our triangles. I need to figure out, well, I have sine alpha, but I don't have cosine of alpha. I can get that from this triangle. I have tangent beta, but I need cosine and sine, so I really need to draw this triangle. So let's draw our triangles just like we started off at the beginning of this unit. Use Pythagorean theorem to determine other missing values, and then come up with our deeds. So check it out. I drew the first one. Sine of alpha is 5 over 13. Sine is SOHCAHTOA, right? Sine is opposite over hypotenuse. So I have sine of alpha is my opposite over my hypotenuse. And sine of alpha is ending in quadrant 1. So here's some random point in quadrant 1. Draw my triangle, right? This is my angle alpha right here. Opposite is 5. Hypotenuse is 13. The way I can find this value is by my Pythagorean theorem. So 5 squared plus 12 squared is 13 squared. And I'm going to use this information and go back to SOHCAHTOA and find out not only did I need sine alpha, but I need cosine alpha. So I'm going to use CA to figure out the rest. Similarly, CAH, cosine of alpha is adjacent over hypotenuse. That's going to be 12 over 13. I'll write that down in a minute. Similarly, I got to do the same thing with this tangent guy over here. So boom, tangent beta. Beta is the angle that ends in quadrant 2. So you could draw either this angle beta or this angle beta. At the end of the day, it doesn't really matter. But tangent, TOA, T is opposite, tangent of alpha or beta is opposite over adjacent. So opposite of this guy is 24. This is in the positive direction, so it's got to be positive. Adjacent is right here along the x-axis, 7. But notice that 7 is going in the negative direction. So this guy has to be negative. And then also by Pythagorean theorem, we would get that this side length is 25. Using that information, right? Sine of alpha is 5 over 13. That was given to us. Cosine of alpha is 12 over 13 from this image over here. Similarly, now that I've got all my sides labeled, sine is opposite over hypotenuse, so 24 over 25, and cosine is adjacent over opposite over adjacent over hypotenuse, so it's negative 7 over 25. So now I have this information, right? I had to figure out what did I need? How do I get it? Okay, I'm still not done. Now that I have these values, I can finally use my identity. So there's a little bit of back work in this one. Again, here's the values that I have from my little images that we drew, right? So we're going to expand cosine of alpha plus beta. So here is our identity, right? The sum identity. Cosine of alpha plus beta is cosine alpha cosine beta minus, remember opposite, sine alpha sine beta. Now I have all of these things. I can just plug them right on in. Cosine of alpha is 12 over 13. I'm going to plug that in. Cosine of beta is negative 7 over 25. So I'm just plugging these guys in. I actually didn't even have to find alpha or beta. Sine of alpha times sine of beta. Sine of alpha is 5 over 13. Sine of beta is 24 over 25. And if I reduce this large numbers, I would get a common denominator of 325. Negative 7 times 12 is negative 84. 5 times 24 is 120. So if I combined these, since they have the same denominator of 325, I end up cosine of alpha plus beta is negative 204 over 325. So this one had a little bit of work, right? To recap, we had to figure out what did we need. We had to draw a picture to find out what we needed. And then we used our identity, something that you'll be a little bit more comfortable with now, to find that exact value of cosine of alpha plus beta. So this is where I'm going to end it today. Just to keep things light, easy, and breezy, we'll have like 3 more problems to go over tomorrow, and we'll finish up these identities. Right now, we've just focused on cosine. Tomorrow, or not tomorrow, the rest of this week, we will also develop similar identities for sine and tangent. As you can guess, they're going to come in super handy as well. So for today, here's your homework number 6. I gave you 9 problems. They're due Sunday. Some of them are so lickety split, but I want you guys to get in that practice. All right, so I will catch you guys later. And I hope you guys are having an awesome day. Bye.